Hi, I hope you are doing well. In our last video, what we learned? In our last video, we learned how we calculate figure of merit and Poloid half maxima. Okay, so now in my last video, I told you that today we'll learn how we can calculate the resolution. Okay, so it's very easy to calculate resolution. So mm, there is a equation of resolution process of calculating the resolution. Okay. So the resolution R lambda is equal to actually uh, um, del minimum divided by del peak, lambda peak. Okay. Okay. So actually, is the easiest thing to calculate. Okay. So let me clear it. How you can calculate the resolution. Okay. So actually, what is the resolution of a sensor? Actually, I can tell you what is the resolution of a sensor. Actually, you can see that this is, for example, the curve of 1.41. Okay, and let me tell you that this is the curve of 1. Maybe 42, and there is some a difference between these two peak, right? So that's how we calculate actually wavelength sensitivity. So from here we calculate wavelength sensitivity. For example, the wavelength sensitivity of between these two refractive index is 1000. Okay. Okay, so this 1000 refractive index, sensitivity is for uh, one refractive index sense. Okay, but we need we want to know that uh, how much change can affect how much change um, what's the minimum change of refractive index can sense a sensor. Okay, so I can show you here. From here that this is showing that the resolution is 1 into 10 power minus 4. So actually it's telling us that for 1.32 1.32 refractive index, only change of like 0.0001 0.001 change of refractive index can sense the sensor actually. So if the resolution is low, then it cannot change very point of change actually. Okay, so here you can see that the sense of the refractive index of this two refractive index is 0.01, right? So for 0.01, um, the the sensor is showing actually how much sensitivity actually 10 wavelength change, right? So for 0.01 change of refractive index showing the wavelength shift of 10 nanometer. Okay, so if we change 0.001 refractive index, the wavelength change will be actually 1 nanometer actually. Okay, so uh, actually the resolution tells us how much the a sensor can actually uh, sense the minimum change of refractive index. Okay, so that's the thing of resolution. Okay, so it's very easy to calculate resolution actually. Okay, so here you can see that the equation of resolution is actually so let me tell it. Okay, the equation of resolution is um why okay, here the resolution of equation of resolution is R lambda is equal to del m is equal to del lambda minimum divided by del lambda peak. Okay, there you can see that the equation of wavelength sensitivity is actually very similar to this equation, right? So here you can see that the if we change it like this, okay, from here, what we can do, if we change it like del lambda minimum, min minimum divided by lambda peak, peak divided by del Na. So this is actually wavelength sensitivity, right? So the equation of resolution is actually something divided by wavelength sensitivity. That's the thing actually. In Excel, how we can calculate the resolution? To calculate the resolution in Excel, we can write R is equal to 0.1 divided by just wavelength sensitivity. That's the thing. Okay. So this is 7.69 into 10 power minus 6. Okay. So in our paper, we can see that for 1.41 is actually 8.33 into 10 power minus 6. So it's okay. In our case, it's 7.69 into 10 power minus 6. So the lowest resolution is the result is the best. Okay. So the resolution will the minimum resolution. Okay. If the resolution is low, then the sensor performance is good because uh, it's telling us that the minimum change of refractive index can sense the um, uh, sensor. Okay, okay, that's the thing. So we need lower resolution. We need a lower FWHM, and we need actually higher wavelength sensitivity, higher amplitude sensitivity, um, as well as we need higher FOM. Okay, thank you. So this is actually how you can calculate the resolution. And another thing I told you that we will learn some advanced thing to do. Okay, so okay, so to analysis some advanced thing like sensor length. So sometimes some literature shows some sensor length. So how you can calculate the sensor length? So let's say the ALS is equal to sensor length. So sensor length is equal to actually 1 divided by maximum loss. Okay. So how we define the loss actually? Um, okay. So okay, alpha. Um, so maximum loss. uh, Okay. This is actually the um sensor length. Okay. For this case, you can see that the maximum loss is kind of 25, maybe uh, 28, let's say 28. So if the maximum loss is 28, then the sensor length is equal to actually 1 divided by 28. So this is actually per centimeter, right? So the sensor length unit will be centimeter. So sensor length is equal to 1 divided by 28 centimeter. This is the maximum sensor length. Okay. So operating range is 1.32 to 1.44, and the maximum sensor length is 1 divided by 28. We cannot uh, make more longer than 1 divided by 28 centimeter of our sensor. Okay, this is actually sensor length. How we can calculate sensor length? So we also can calculate sensor length for per wavelength. So this is for 1.42. So for 1.43, maximum loss is maybe 20. So then for 1.43, the sensor length is 1 divided by 20. That's the thing. Okay. So this is how we calculate the sensor length. And there is another thing we can learn for advanced calculation. Um, that is maybe okay. So okay, another thing we can learn actually, that is actually the polynomial curve. How we can calculate. Okay, in my next video maybe I can tell you how we can draw the polynomial curve in Excel. Okay, thank you for today.